Thanks a lot, everybody. It's great to be back in KL. It's great to be here. And what I'm going to talk to you today is about how to make the cloud more secure through better cryptography. So I don't think it's any surprise to anybody here that the world wants to move to the cloud. If you look at numbers from analysts, they're all saying that people are moving to the cloud in droves, and because of iPhone applications, Android applications also using the cloud for data storage, it's becoming where the bulk of our applications are. But on the other hand, most people in the enterprise also say that the cloud makes them very nervous, that security is the top reason why they're hesitant about the cloud or won't move to the cloud. And the real worry about security is this. If I'm a cloud provider and I've got all your data sitting on a server, if that box gets owned, then everybody's data is compromised at the same time, and that could have big consequences to a business. So how do people deal with this problem today? There are a bunch of ways. So the first solution is not to use the cloud, of course, and a lot of big companies are still in this camp, especially large financial firms. But a surprising number of people just like to stick their head in the sand and leap into the cloud because it makes them it's cheaper and it allows them to focus on other things. There are other solutions though. You can keep all your data encrypted in the cloud and then decrypt it when it gets to the client. There are a lot of problems with this. I'm going to use, as an example, email archiving a couple of times through this presentation. Imagine that you've got terabytes of email up on the cloud, and now you want to go search through all that email. Well, if it's all encrypted in the cloud, and you need to decrypt it on your PC, in order to search terabytes worth of email, you'd have to pull it all down to your laptop, decrypt it there, and obviously that doesn't make any sense to anybody. So that's not really a great solution, and so people don't really do this. Plus, obviously, the vendor would generally have to support it as well. So a fourth solution is to actually encrypt server-side. And there are a bunch of solutions that look like this. So, for instance, a couple of companies provide boxes that allow for multi-tenant disk level encryption. And basically, the idea is that when you identify a user and you've got their password or whatever credential, that's used to decrypt all that user's data on an as-needed basis. The problems with this, all your keys are still sitting over there, and you can provide more separation from your application of the keys, but you still have a little bit of a concern that you're just shifting the problem around. But these solutions do work pretty well if you handle them properly. The biggest challenge for a lot of people is these solutions are also ridiculously expensive, so very few cloud providers are actually using them and integrating them into their solution. So that basically is the problem. If I'm using Gmail for my email, there's no way that I can benefit from them encrypting all my data because they're not doing it, they're not giving it to me as an option. I can't even pay for it. So the fifth solution, which is what we're going to talk about today, is encrypted search. The idea is being able to actually encrypt all your stuff, leave it on the server, and search it on the server even though it's actually still encrypted. So, if somebody sends you an email, it's going to go to the server, but in our new scenario, what's actually going to happen is that email is going to go to a proxy first that will encrypt the email, and an encrypted version of the email will go to the cloud service that you're using. All right, so what happens when I actually want to go read my mail? Well, if I talk to my little proxy, then I get a legitimate version of the email. But if I skip the proxy and talk directly to my cloud provider, what I get is gobbledygook. It's the encrypted version of the email. And so, the cloud provider that you're using in this case, if they don't have control over the proxy, they don't have controls over the keys that was used to encrypt the email, they can't see any of the contents of your mail. So now, that's all pretty easy to do, but the question is what happens when we want to actually search our email? Again, we don't want to have to download it all to search it. Well, what we do is, we send our search to the proxy. So let's say we're searching for messages that contain whatever. The proxy then encrypts the search term and sends the search term onto the server, and the server searches through the encrypted data for this encrypted search term. Any results come back, they get sent to the proxy decrypts them, and you get the view of your email fully decrypted just of your search results. So to most people, this sounds like magic, like it's not technically feasible to do something like that, but it actually is real. There are a few solutions out there that you could actually buy today. Navajo Systems was doing this kind of approach on Salesforce so that they could give people using Salesforce, let them encrypt their data. So Salesforce bought them, and the other two guys are primarily focused on email right now. So there are a lot of challenges that are fairly easy, but are very important that we won't spend time on. The first one is protocol parsing. So if you're going to build this proxy, it has to understand the entire protocol, which is pretty easy for something like SMTP or POP. It's actually really difficult for IMAP because IMAP supports asynchronous two-way communication, and it's even harder for the Exchange MAPI protocol. And then if you're doing web apps like this, like imagine building a proxy to make sure that you handle Gmail properly. So yeah, they use XML, which makes it a little bit easier, but it can shift on no notice, and they're not going to call up they're not going to call you up and say, hey, we're about to make changes to the way the web client works. So there are some challenges there. Another challenge is how do you do authentication and key management? The simplest way to do this kind of thing is to have one proxy for a company that encrypts and decrypts everything, but now you've got to authenticate to that thing, and do you want to use per user authentication or per user encryption here? And then how do you handle key rotation, key storage, key expiration, revocation, all of those things? Typical problems though, and that's not what I'm going to talk about today. The third challenge is the data encoding. So when you're dealing with a website and you're looking at data, you're often dealing with numbers or text. And when you encrypt those things, generally encryption operations give you binary data. And you have to encode that data in a way that will actually not break the program that you're sticking the data into. And that's, there are some challenges to that. We'll look at that problem a little bit today. So let's look at encrypted data types here. The easiest thing to do is exact match encryption, which means that when you're searching, you're only going to hit when the search term is exactly the same as the data field you're looking at. So, and this applies for everything. It could just think about it as you're encrypting data that we're storing in a database for right now. And so we're going to encrypt the entire field, and we'll only get a match when the entire field is the same. We'll talk a little bit more about this. Then you can actually do order-preserving encryption. So if we are thinking about a database, for instance, we may want to be able to sort our results. So if we're getting that email and we want to sort by date that received, we can actually do that if we use an order-preserving encryption routine on the date function. The problem with this is that it leaks a lot of information, so even the best known order-preserving encryption scheme gives a lot of information away just because of the ordering of items. So you can, if you leak one piece of information, then you may learn other pieces of information. So it's still a valuable primitive. You just got to know what you're getting into. A third option is homomorphic encryption. Homomorphic encryption actually allows for math operations to occur on two encrypted values without having to decrypt the values. And where this could be useful, if you think about it again in a database context, if you want to sum an entire column of numbers, you can totally do that and not have to decrypt the column of data. This tends to work pretty poorly in very large data sets, but is pretty cool. But the most important, I think, is searchable data fields, where the field, instead of being an exact match, having to exactly match, we can search within the data field. So, for instance, when we're searching through emails, schemes today, as we're about to see, are usually going to leak information about what's in the data field. And the biggest problem with this is that people have not been able to implement wildcard searching in data fields, so you really can only search for a word at a time. So, all right. What I'm going to talk about today is I'm going to start by explaining the exact math stuff to you, which is going to give you context, so that I then talk about the searchable stuff later. To do that, just a very little dollop into the cryptography. We're going to be talking about something called a pseudo-random permutation, which is a one-to-one function that changes its data so that it's indistinguishable from like a random output. And really, what this is, just think of it as AES, but there's a little bit of a difference. AES is a PRP, or is believed to be a PRP, but the difference is that if we only were to use AES, we could only process 128 bits at a time, because that's the block size of AES. So we need our primitive to have the property that it can handle arbitrary data inputs, but do the same thing that AES does, which is scramble the data. And there are a bunch of different techniques we can do that. An easy one is to use something called malleable encryption to solve this problem. It's irrelevant for the purposes of our discussion today, but I can give you a really easy construct that can do this if you're really interested, or I can talk to you about other things that will give you the same basic guarantees. But let's look at how we're going to use our pseudo-random permutation. Imagine that we're on the proxy and we get this SQL statement where we're going to select everything from a table if the column equals hello. So the proxy will get this and need to translate the term. So it uses our encryption operation with a key, right? The key that's specific to the customer. It could be the end user, it could be the company. and it's going to encrypt that, just like AES would encrypt something, but you notice it's not a 28-bit value. So it encrypts that, and then base 64 encodes the output. All right, then it's reconstructing the statement and actually sending that off to the database. The database will give us encrypted results, and then the database, whatever it gives us, we can use the decryption operation with the same key to get the original text back. So that's basically how it works. And here's kind of a very simple example of how encrypted data could possibly look in a database, and it's going to illustrate some of the things that we should be thinking about. So here we've got 3 fields, a unique identifier, which is the primary key of this table, a physical address, and the answer to a secret question. So a few things that we notice right away is that we've got 2 different entries that share the same address. That's a huge information leakage right there, right? You know that there's a relationship between those 2 fields. The other thing we notice is that the 0G for the third ID there is the same as the secret question for the first row, which means definitely that the answer to that secret question is just a number. And as a matter of fact, we know that it's like a 1 character probably. So we're leaking a lot of information here, the length of data, relationships between data. This kind of thing, again, is often acceptable. People don't really mind if some of this data leaks, but one way we can address this problem is by using a different key for every column of data. So if we did that, we'd never be able to see a relationship between what's in the ID column and what's in the secret question column. So we could also use 1 key per row, but that basically destroys searchability. So if you think about that, when we encrypt a search term, we just want to send 1 search term over. But if we had to encrypt the search term once for each row that it might possibly be in, and we've got millions and millions of rows in our database, that isn't going to work very well. So we really can't get around the leakage problem within the same column, at least using this approach. And one other thing to notice is that if we encrypt hello with a capital H, we're not going to get the same result as if we encrypt hello with a lowercase h. So when we're searching, we need to take that in consideration if we want our searches to be case insensitive, which generally we do. And we'll look at that in a minute. All right, so that's exact match searching here. Now we're going to go on to fully searchable stuff. And I'm going to start by showing you a typical approach, the typical approach that these companies in the field are taking. And just imagine that we're talking about email messages, and we're looking to apply encryption to the body of email messages so that we can search it in the cloud without having to pull it down. So this will be our example email for now. If you notice, it's got some repeated words in it, this and this, although it's capitalized the first time, it's not the second time. It's got some punctuation in it as well, and as well as it's got 2 of the same words. So what typically happens is that we use our same encryption primitive that we were talking about, our PRP, and we encrypt each word independently, and then we leave the punctuation, the spaces, stuff like that intact, unless we consider it part of the word. So you notice the apostrophe we encrypted, but the comma and the period we didn't, because we didn't consider those part of the word. We don't want to have to search those things. All right, so now let's see how a search would work. So this is what our email looks like on the server. Now, if we search for the word example, which is in there, it was probably the 4th word. the proxy is going to encrypt that search term, send it off to the server. The server will return this message because that word is in there. Although, again, we have to worry about what the server's notion of a word is. Does it actually ignore the equal signs? Some systems actually won't return a hit on this because it tokenizes the words differently than you're expecting it to do. But just assume for a minute that this actually hits because it usually will. And then if we take another search term for a word that's not in this email, similar thing will happen. It'll get encrypted. The message will get searched, but it's not found in this message, so nothing happens. This message won't get returned. Okay, so that's what a lot of these vendors are doing today, and let's see how well it works. So the first thing to notice is that there's an awful lot of length leakage here. We can see the length of every word. We can start making guesses as to what these values actually are, not just based on their length, but relative positioning. So, for instance, as well as is a pretty common phrase. So if you see, the same two-character value, 2 words apart, there's a better chance that it's the word as than the word is, for instance. So you could see that you could use statistical analysis over a lot of ciphertext to start to figure out what a lot of the data is in here. So also, we are leaking a lot of the word ordering and punctuation. So the fact that we know that the sentence stops here, that a comma is there, all of those things can provide us more information about what actually is said in the text. So let's look at the word this. We notice that it's capitalized in the first word, but later on it's lowercase. So it actually encrypts to 2 different ciphertexts. That again means that we can't have a case insensitive search this way. And if we tried to normalize the data, for instance, by lowercasing everything, then we would change the plain text to do that. We would have to change the plain text to do that, which generally isn't acceptable. And we talked about the double equals, but the other thing, since we're base 64 encoding here, we may break what the application knows about word boundaries, because most programs will treat plus and a / as you'll see in the highlighted things as word boundaries, and they might not even accept that text at all, depending on what the field is. So this is something that you've got to be able to deal with as well. All right, so let's talk about my new approach to doing this. We've got the same plain text as before, but it encrypts entirely differently. One thing you'll notice is that the message is longer. All right, so there's one big block here, and then a bunch of smaller words there. The first big block is actually an encryption of the entire message. So we're talking about using our PRP to encrypt the message. The other guys are doing it 1 word at a time. We're doing it 1 message at a time. So we encrypt the whole message, and that's the first part of what you see. Then the bottom part is actually an encrypted index. So what we're doing is we are taking every word in the message. We are first normalizing the word. So let's say we uppercase everything. And then we're going to create like a unique value for each word. We're going to do this through what's called a MAC, and a MAC is a keyed hash function. So think of it as something like MD5 or SHA-1, but it takes not just your data to hash, but a key as well that is secret, so that nobody can forge values. So instead of using our PRP, we're actually going to use this hash function, basically. We have to give it a different key than we gave the PRP, so we've got a second key called MK, and we're using that to process all of the normalized values. So then, we're going to actually take the output of that MAC and truncate it to a smaller value, because we actually don't mind if we occasionally get false positives. We'd rather save space. So typically, say like HMAC SHA-1 will produce 160 bits of output. HMAC SHA-256 will produce 256 bits. But you really don't need to have that much per index term. You can get away with 10 bits if you really want to. The only downside is that occasionally you'll look for an email and there will be a hit returned and it doesn't actually have your search term in it. That's the worst that can happen if you truncate. And the more you truncate, the more likely that is. If you don't do any truncation at all, it'll never happen. If you truncate to 16 bits, you'll barely ever notice it. It'll happen once in a blue moon. Okay, then we're going to sort the index of words. We're going to remove duplicates. So if the word as was in there twice, we're going to we're only going to keep one index value. They'll both be the same. And then we're going to encode in our encoding scheme, which will leave base 64 for the moment, although we'll replace the slashes and pluses with dashes and apostrophes. All right, so what ends up happening is that the proxy does all this work on the search terms as well, so we can solve a lot of the problems that other people were having with these search terms. So the case insensitivity thing, the apostrophe, does it match John or John's? All of those things are fixed here. The proxy just has to have the MAC key as well, so it can recompute the search term. So going back to our example, if I'm searching for the word example, we'll create a different encrypted search term, and this message will get returned because that search term is sitting right there. It's the first thing in the index, but example, remember, was not the first word in the message. This was the first word in the message. So it just happens to be that the word example comes first in my index. So the word this, because of the normalization we're doing, both of the instances of this are represented in this index by that highlighted in blue encrypted search term. So this approach has a lot of advantages to the other one we were talking about. We still leak some information, though. One is the total length of the message. We still can clearly see how long the message was. The sizes, when you decode the message from base 64, the size will be exactly the same as the original message. We can also figure out how many unique words were in the message. The last time we could figure out the total number of words in the message. We still are giving you the number of unique words in the message. And we are also still leaking whether the same word is available in multiple emails. That's, like we said before, that's really unavoidable if you really want to be able to search with techniques today. But the last two of these things will go away a little bit as we add in support for wildcards. So I'm going to show you how you actually can take this technique and do full wildcard searching if you really want to. And all it really requires is more indexing. So I will give you the steps on how to do this. And I'm going to start with a much smaller example email here. So what we're going to do is just index every desirable term that is a regular expression that matches this mail that we would ever want to hit. So in this case, we would create an index for all of these things. And then when somebody searches for any one of these things, this email message is going to hit. So we can see that what happens is we mac all of these things. This is what we get. Then we are going to sort this thing so that we take away ordering information and you know, then we are actually going to encrypt the plain text, and so this becomes our message. And so now when we want to search for something with a wildcard, so exa star, which should definitely match the word example, we are going to send that to the proxy. The proxy will encrypt that search term. We call it encryption, but it's really using the MAC to generate the search term. It's going to send it to the server. The server will find that right there at the bottom. So if we then go to search for something else, like miss star, which is not in the email, so maybe we're looking for the word mission or missing or whatever, that's just not going to hit because it will give us a different encrypted search value, which isn't in this list. Okay, so we've handled really simple wildcarding. Obviously, we can do a lot more. So for the word test, for instance, all of these are wildcards that might match the word test. We can use the same technique to handle multiple word searches. So usually what people would do is, you know, if you look at how people search today, they will usually search for one word wildcarded or for multiple words that are exact words. And so, you know, we will use like 2 or 3 word groupings. We'll index all those after normalizing them all, and then do wildcards on a single word level and throw out the small wildcards too. Like most people don't ever search for T star, or even you know, TE star maybe is a little more common, but usually it's 3 or more, and most people don't use even complicated wildcarding. They just use the asterisk, and they use it at the end of a word, not at the beginning of the word. So the approach that we used in the first example is usually good enough for most people if you handle multiple words as well. So a couple more considerations with regard to this technique. If you, you know, we've been talking a lot about base 64 encoding being tricky. Even if you replace the bad characters with characters that usually are acceptable within word boundaries, you can end up with them at the beginning of a word or the end of a word, and that might not tokenize right on the server side. So I actually recommend using a 32-character alphabet to encode instead of a 64-character alphabet. If you do that, things will work out a lot better. And I also recommend, you know, for a good trade-off between message expansion and false positives, 15-bit tags are really good, and they're going to add 4 bytes for each tag to the message, 3 to encode the 15 bits. If you're using base 32, it's encoding 5 bits into a single byte. So 3 bits per tag plus the space in between tags. So you'll give up 4 bytes for each search term that you want in the message. All right. Also, many of these terms are going to overlap when you're doing wildcarding, especially the short wildcards. It actually won't be as bad as it seems in terms of message expansion. You'll get a lot back. But if you do the like full wildcarding, across the English language. I went to Dict on my local machine and did the analysis. It takes on average, you've got on average the words in the Dict file are 10 characters, which seemed really high, but that's what it is. I'd say common usage, it's probably a lot lower, but if you go to the dictionary, 10 characters is the median. You do the analysis over the whole dictionary, and it's 62 and a half wildcards per word on average is what you would expect if you were doing full wildcarding just with the asterisk. That obviously is a 4x expansion, that's not great. But if you use the simple approach, which is just something star, without even taking into account duplicates, and including the small globs, that will be less than 4.5 times message expansion is what we're seeing in practice. So about a 4x if you got a terabyte of email sitting there and you want to do wildcard searching, then the message expansion will be about 4x for simple wildcard searching, which is not too bad. 3 extra terabytes is not that expensive. All right, so the last consideration here is that key rotation is actually a pain in the neck when you're doing an encrypted index. So if I decide that I want to change keys in order to because the key got compromised, well then I'm in a pretty bad state because I need that key to stick around until I can re-index everything, which could take me an awfully long time. So key rotation in this scheme requires re-indexing everything server-side, and that's probably always going to be true with every scheme out there, but certainly a real operational challenge to any of these schemes. So that's it, pretty short, just to kind of reiterate, what we did was provide a way to allow you to add your own storage to software as a service applications living in the cloud, even if you don't have the support of your provider. So you can do this with Gmail, you can do it with whatever if you really want to do it. Plus you can do it in a way where you can actually search all that data without having to download all of it to you. And then we talked about search to make it leak less information to support wildcards. And that requires a trade-off with storage, but makes it really functional. So that is everything in a nutshell. I'm happy to answer questions if there are any. Yeah. Oh. Yeah.
The problem of cross-mail leakage of the same words being used in several emails.
Yeah.
Isn't that a pretty big problem? Because if I'm an attacker, and apparently I'm very gifted because I managed to own the cloud box, all I have to do a search is send an email. I can send an email which I can identify because there is a really long string in it or something. I put my own chosen keywords in it and I can search your entire data set.
Yeah, absolutely. So you can leverage that if as long as you have the chosen plain text attack, you can, still get enough volume of plain text that you can absolutely start. That's true with any of these schemes right now. So, that's why the key rotation being a problem is because you want to be able to limit the damage when you determine that there is an attack. So that's absolutely a problem with any scheme like this. And frankly, you know, this is kind of cool. It's nice when you want to, you want to be able to use the cloud, but they're not supporting it. But I'm not saying actually that it's better than the alternative, which is the cloud provider actually buying one of those big boxes to, handle all the encryption at a disk level in a multi-tenant fashion. It definitely has its advantages, although again, the security of the key material is still an issue there too. So it's not a perfect world. Is there anything else? Yeah.
You mentioned about there's a wildcard search, right? So if the wildcard become more complex, so the indexes that you have to put into the email contents may actually exceed your original email contents. Would it be the case?
Because of the volume, I'm not sure I understood the question. It was about the wildcard expansion, is that right?
Yeah, the more wildcards that you provide, the more indexes that you will incorporate into the original mail.
Right.
So if the mail contents is very small, but the wildcard probability is very huge, then the contents of the index may, exceeded the original string.
Right. So when you do this kind of thing, that's a great point, and hopefully for those who didn't hear the question, I'll explain it in my answer. But when you use like one of these encrypted proxies to deal with somebody's SaaS application, you have to be cognizant again of what's likely to happen to the data on the back end. And if it's going into a database, a database field, a lot of the times the field will have a maximum storage size at which point your SOL, if you try to stick more data in that field than it will take. And in that case, you got to make the decision about how you're going to handle that. Usually, you're not going to do any wildcarding on a field like that. You might not even do any indexing at all. You might just leave it to exact search only, and then you're just kind of stuck with that. The other thing that you could do instead is leave the index on the proxy so that just kind of not put it all the way on the server, which would allow you to still retrieve the right fields, but you're doing like the filtering once locally, and then kind of completely rewriting the query going to the server, which actually also addresses the issue that we were just talking about if you want to do that every single time. So, you basically just leave the entire contents of the indexes on the proxy. But, either way.
Okay, one more question. Right?
Sure.
Because just now you only mentioned about word. How about search by phrase and the ordering? So if I search something like vice president, right? Mm-hmm. And then your indexes based on vice and president. Mm-hmm. So the ordering may actually can't find the phrase that you are looking for.
Yeah, so when you go through your normalization and indexing process, you have to take that into consideration. So if you want vice-president to work and you want vice-president to work, then when you normalize, you have to look and say, well, it's got a dash, but I want to treat it, I'm going to index it as vice and president, two separate words, and I'm going to index it as vice president together and with a dash. So, if you wanted to hit all those possibilities, you'll see a little bit of extra expansion. And we do that in our kind of test bed, and the expansion's pretty minimal. Again, with everything we're talking about here with kind of the simple wildcarding, it's about 4 to 5 times expansion is what we typically see. Yeah.
the more I'm thinking about this, the more I have a very fundamental question. Basically, this is about securing SaaS, software as a service.
Sure.
If I'm understanding this correctly.
Yeah.
The nice thing about software as a service is that the software as a service is that the software, the application, all the logic is somewhere in the cloud and it's always accessible. In this setup, you have a proxy, which is presumably not part of the cloud.
Most of these vendors, which I'm not affiliated with any of them, by the way, but they're all offering either go put the proxy wherever you want, as a, they sell them as a VMware image, or they have their own cloud-based proxies that, so you still don't have any infrastructure to manage.
No, but from what I gather, this whole proxy thing is a way to separate the keys from the ciphertext material.
That's right.
So presumably you don't want the proxy in the cloud because you're assuming the cloud is ownable and you don't want...
Yeah, well, that's up to the companies that are having the problem moving to the cloud, right? So if you talk to Bank of America as an example of somebody who was very reluctant to move into the cloud for exactly this reason, they would probably say we want to host the proxies internally, in which case, it would be very easy for them to do. They'd only be managing kind of one thing instead of having to manage, for instance, Microsoft Exchange, which is really complicated to manage. So they can still leave that complexity to somebody else and just have to keep these little proxies running, which, even if they do die, who cares? There are 6 other ones doing the same thing. Other people don't even want to deal with that, and they would be happy enough having their risks spread across 2 providers instead of just 1.
Just to get back to my, or actually just to start my question.
Sorry about that.
Basically, the idea of a proxy is only makes sense if you want to separate the key material from the ciphertext.
Right, right.
And you're using this in the situation for software as a service. But the whole thing about the software, it only works if all of the communication towards the software goes through the proxy. So all of the software as a service, the entry point is shifted towards a proxy.
Yep.
So your software as a service is no longer a software as a service in the cloud, it's a software as a service on your proxy.
Yeah.
Doesn't that defeat the whole purpose of software as a service in the cloud? Basically right now you're creating a software as a service locally with storage as a service in the cloud.
Well, look, maybe you see it that way. Most people that I have talked to about this don't, right? I mean, they see the value of the cloud is, allowing them to focus on their business by putting these complex applications in somebody else's hands, not having to worry about the fault tolerance, like the ops and so on. And you can do that here still. Now, again, you alluded to another really great point, which is you still have to have the right controls in place to make sure that you deal with people who are going directly to the, let's use Salesforce as an example. If we're all using Salesforce and you log directly into it instead of to our proxy, that's a problem, and that's what I was hinting at earlier with the authentication bit is a challenge, because really what you want to do is only give people authentication capabilities to the proxy and have the proxy store all their authentication capabilities to the server. The other approach I've seen is, you actually have a process that sitting on the proxy that goes in and starts decrypting data that isn't encrypted. But, that's silly.
If you're going to be trusting the cloud implicitly because you want to outsource everything, including the proxies, why not just combine the proxy back into the cloud application?
Well, because it's additional risk, right? So if I have one of those vendors hosting a proxy and I've got Google hosting my email, both Google and, email is a horrible example, but both Google and one of those proxy providers would have to be compromised. So you're reducing your risk that way. So. That's how people see it today.
But in that case, you would only have to own the proxy, and you would have everything.
Yeah, but much smaller attack surface. So it's hopefully a lot easier to secure. So, but yeah. Okay, anything else? There's a lot more than I expected, actually. That's good. No, that's good. I figured everybody's eyes would glaze over and they would fall asleep, but instead they're playing with their phones. It's good. Yeah, another question.
I've got a totally naive question. I apologize for that.
Yeah, no worries.
I mean, in theory, we're all learned people here, either security practitioners like you or security users working for organizations. We all know that we should have the encryption to protect data, especially when we go public cloud.
Yeah.
Here's the stupid question. Who's actually going to do all this?
Who is what?
Who's actually going to do the encryption? The data center's not going to do it. The provider's not going to do it. The vendor the user has no clue, and you get the idea. Who's mechanically going to encrypt that data?
Yeah, so
half the way you said
the premise here, that's a great question. I think the premise here is that the cloud provider generally isn't going to do it, right? The SaaS companies don't want the extra expense. They don't want to have to deal with the key management. They don't want to do it. That's right. They don't know anything about security anyway, right? So the burden is on you as the customer to come up with a solution if it's important for you for that data to be encrypted before you put it in the cloud. And that's really what this kind of approach is meant to handle. So either you do the encryption before it gets to the cloud, or you find a second cloud provider that's focused really only on doing that encryption for you. So, yeah, exactly. So the most forward-thinking SaaS provider is actually Salesforce, because they bought a company doing that. They could offer it to their customers, and they can say, look, we've got our infrastructure storing your data. We've got a separate infrastructure that's that's encrypting your data. They're totally different places. Everything's different about them. And oh, by the way, if you want to encrypt your data yourself, have at it. We don't care. We don't need to have any access to it. That's much better than pretty much any other cloud provider today. Hopefully that will change. We'll see how it goes. But in the meantime, you can do it yourself. You're just, as this talk has shown, you're going to lose a little bit of functionality, especially with the vendors that are out there today. Although, they're, hopefully they'll get more functional as time goes on.
Thank you.
Yeah, thanks. Okay, well, thanks a lot.
Thank you, John Viega.